Hey there. Most people click away quickly. If you haven't, you're already the kind of person this channel is made for. Subscribe, and let's begin. You begin by tracing the life of a star more than 8 times the mass of our Sun. For millions of years, it has been balancing the outward pressure of nuclear fusion with the inward pull of gravity. Within its core, hydrogen atoms fused into helium, releasing energy that counteracts the relentless pull of the star's own mass. Over time, hydrogen is depleted, and the star gradually fuses helium into heavier elements such as carbon, oxygen, and eventually iron. Each successive stage occurs more rapidly than the last. As the core becomes denser and hotter, the fusion process exhausting increasingly unstable fuels. Iron represents a critical point in this progression. Unlike previous fusion reactions, fusing iron does not release energy. Instead, it consumes it. You recognize that the star's core, having accumulated iron, reaches a state where outward thermal pressure can no longer resist gravity. The core's mass exceeds the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, and collapses within a fraction of a second. Electrons and protons combine under the extreme density to form neutrons, releasing neutrinos in a brief, intense burst. This process, called neutronization, converts the core into a sphere of almost entirely neutrons, with densities exceeding 100 trillion times that of water. Gravity drives the collapse inward, yet an extraordinary force emerges from quantum mechanics. Neutron degeneracy pressure, arising because no two neutrons can occupy the same quantum state, resists further compression. This pressure halts the collapse when the core reaches a radius of roughly 10 to 15 kilometers. You can imagine the scale. A mass greater than the Sun compressed into a sphere smaller than a city. The sudden halt of the infalling material creates a shock wave that travels outward, colliding with the star's outer layers. This shock wave is powerful enough to expel those layers into space, producing a core collapse supernova, one of the most luminous events in the universe. As the outer layers expand and cool, you observe elements forged in the star's interior being scattered across space. Oxygen, silicon, and iron enrich surrounding interstellar clouds, seeding future generations of stars and planets. Observationally, these remnants are seen as glowing nebulae, like the Crab Nebula, where high-energy particles continue to emit light decades after the initial explosion. The neutrino burst from the core collapse precedes the light by hours, and these elusive particles provide direct evidence of the processes occurring deep within the star. Detectors on Earth have recorded such neutrinos from nearby supernovae, confirming predictions of stellar evolution theory. Simultaneously, you note the rapid rotation of the newborn neutron star. Conservation of angular momentum dictates that as the core's radius shrinks dramatically, its spin rate increases. Even a moderate rotation of the progenitor star translates into a neutron star spinning several times per second, or in some cases, hundreds of times per second. This rotational energy plays a crucial role in the star's subsequent evolution. Alongside rotation, magnetic fields become concentrated. The core's magnetic flux is conserved as it collapses, amplifying the field to extraordinary strengths. Fields of 1 trillion to 1 quadrillion Gauss can emerge, dwarfing anything achievable in laboratories on Earth. These magnetic fields shape the behavior of charged particles in the star's vicinity and govern the emission of radiation that may later be observed as pulsar or magnetar activity. You consider the balance of forces within the star. Gravity attempts to compress it further, while neutron degeneracy pressure and nuclear forces provide an opposing counterforce. The outer layers, expelled by the shock wave, create a temporary void, yet the core remains stable. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons. Within this small sphere, atomic nuclei no longer exist in their familiar form. Instead, neutrons form a degenerate sea, possibly accompanied by exotic particles such as hyperons or a quark-gluon mixture at the very center, though observations are still refining these models. The young neutron star's temperature immediately after formation is incredibly high, on the order of hundreds of billions of Kelvin. Thermal photons and neutrinos carry away energy, cooling the star rapidly over minutes and hours. The initial X-ray emission can be observed by space telescopes, providing data about surface temperature and composition. You follow how the cooling slows as the star emits less energy over millennia, settling into a long-lived state where internal pressure, magnetic forces, and rotation maintain equilibrium. Surrounding the neutron star, the ejected material interacts with the interstellar medium, creating shock-heated gas that glows across radio, optical, and X-ray wavelengths. The dynamics of this interaction are measurable, revealing the expansion rate, chemical composition, and energy released during the explosion. Observations over decades allow astronomers to reconstruct the original supernova, confirming theoretical models of core collapse physics. Each supernova acts as a cosmic laboratory, validating principles of nuclear physics, hydrodynamics, and gravity. You also notice the role of asymmetries in the explosion. Not all supernovae are perfectly spherical. Slight irregularities in the collapse can impart a kick to the neutron star, propelling it through space at hundreds of kilometers per second. Such velocities are measurable through careful tracking of pulsars in the Milky Way. This movement influences how neutron stars populate the galaxy and how they may eventually encounter companion stars, potentially forming binary systems. As minutes pass after the collapse, the magnetic field and rotation establish an environment capable of producing electromagnetic radiation along the star's magnetic poles. These emissions, highly directional and periodic, are later observed as pulsar signals. The young neutron star's characteristics, spin rate, magnetic field strength, and surface temperature set the stage for whether it will evolve into a typical pulsar, a magnetar, or another classification. Each path is dictated by measurable quantities derived from the birth conditions of the core and the progenitor star. Your awareness settles on the interplay of forces that produce this compact, dense object. Gravity, nuclear interactions, quantum degeneracy, and electromagnetic phenomena converge in a stable balance. The neutron star is no longer collapsing. It exists in a finely tuned state where every particle, every quantum, contributes to its structure. Observations from Earth provide the evidence. Pulsar timing, X-ray emissions, neutrino detections, and supernova remnants all corroborate this process. Finally, you consider the immense energy contained within the star. Even in its compact form, it retains a fraction of the original star's rotational and magnetic energy, slowly radiating it into space over millennia. These emissions carry information about the conditions deep inside, offering a direct connection to the physics of extreme matter. As you follow the cooling surface and stabilizing spin, you begin to sense how this newborn neutron star will interact with its environment. Its energy, fields, and rotation will influence surrounding space and the eventual signals that reach distant observers, hinting at the rhythms and structures that emerge as these dense remnants continue to evolve. The neutron star rests in its compact sphere, spinning and radiating, a testament to the interplay of gravity and quantum forces, while the expelled material drifts outward, spreading elements that will someday form new stars and planets. Its birth illuminates the precision of astrophysical laws and the remarkable consequences of extreme density and energy. As the neutron star cools and settles into rotation, you quietly anticipate the patterns of electromagnetic radiation that will mark its presence, opening a path to understanding how these remnants communicate with the universe through light, magnetic fields, and motion. You begin by approaching the surface of a neutron star, noting that the outermost layer is a thin solid crust composed primarily of nuclei and electrons. This crust, only about a kilometer thick, is extraordinarily dense. Atomic nuclei are packed tightly together, arranged in a crystalline lattice, while electrons move freely between them. Despite its small thickness compared to the entire star, the crust governs important phenomena, including the generation of starquakes and the propagation of magnetic fields. The top of the crust is relatively less dense, but as you descend, density increases and nuclei are forced into unusual configurations. Beneath the outer crust lies the inner crust, where density continues to rise and neutrons begin to drip out of nuclei, forming a neutron-rich fluid. This layer is a transition zone in which nuclei coexist with a sea of free neutrons. The behavior of matter here is constrained by the Pauli exclusion principle, which prevents identical neutrons from occupying the same state, producing degeneracy pressure that supports the star against gravity. Observations of pulsar glitches, sudden changes in rotation rate, indicate that interactions between the crust and the superfluid neutrons beneath it are real and measurable. These rotational irregularities provide indirect evidence for the presence and behavior of superfluid neutrons. Deeper still, you encounter the outer core, which extends to roughly half the radius of the neutron star. This region consists predominantly of neutrons, with a small fraction of protons, electrons, and possibly muons. The density is immense, several times that of a nuclear atom, and the particles interact via strong nuclear forces. Neutrons in this layer behave collectively, forming a superfluid that flows without resistance. The protons, by contrast, form a superconducting component, influencing the star's magnetic field structure. Observationally, the cooling rates and thermal X-ray emissions of neutron stars provide constraints on these superfluid and superconducting properties, confirming theoretical predictions. At the center lies the inner core, whose exact composition is still under investigation. Density may reach several times that of atomic nuclei, and matter could exist in exotic states. Theories suggest the possible presence of hyperons, particles containing strange quarks, or even deconfined quark matter, though these remain subjects of active research. Despite uncertainties, astrophysical measurements, including mass, radius, and moment of inertia of neutron stars, allow scientists to constrain the equation of state, the relationship between pressure and density, governing the core's behavior. The heaviest neutron stars observed, around 2 solar masses, set strict limits on how compressible the core matter can be. You notice that throughout the star, gravity is intense and uniform, compressing matter into a nearly spherical shape. Spacetime itself is curved, with general relativity providing an accurate description of how matter interacts with the star's gravitational field. The star's mass and radius determine surface gravity, which can be billions of times stronger than Earth's. Any particle, from an electron to a photon, is influenced by this extreme curvature. Light escaping the surface is redshifted, carrying information about the star's gravitational field. Astronomers use these gravitational redshifts to estimate neutron star masses and radii, confirming theoretical models of dense matter. The crust and core interact through multiple mechanisms. Magnetic fields, anchored in the core, thread through the crust and influence charged particles. Rotational energy affects both layers, and sudden rearrangements of the crust can transmit torque to the superfluid core, producing measurable pulsar timing changes. Thermal conduction is highly efficient along the crust, allowing heat generated in the core or by magnetic activity to reach the surface. Observed cooling curves of neutron stars, recorded in X-ray emissions, reflect these processes and provide insight into internal composition and thermal conductivity. The equation of state is central to understanding neutron star structure. It describes how pressure increases with density and determines whether a star can resist gravitational collapse. Different theoretical models predict slightly varying radii for a given mass. Observations of neutron stars in binary systems, particularly those with precisely measured masses through orbital dynamics, help narrow the possible equations of state. These measurements, combined with X-ray timing and spectroscopy, allow scientists to infer the internal pressure profile and density distribution of the star, revealing a layered interior that matches theoretical expectations. You consider the dynamics of the inner superfluid. In a superfluid, neutrons can flow without viscosity, forming quantized vortices that carry angular momentum. These vortices can pin to the crust's lattice and unpin suddenly, transferring angular momentum and producing pulsar glitches. The timing and magnitude of these glitches are consistent with models of neutron superfluidity, providing a rare observational window into matter under extreme density. This connection between microscopic quantum behavior and macroscopic rotation is unique to neutron stars and can be measured precisely thanks to the regularity of pulsar signals. Electromagnetic radiation originates from the interaction of the star's magnetic field with charged particles in and above the crust. Electrons accelerated along magnetic field lines emit radiation, producing pulsar beams observed in radio, X-ray, or gamma-ray wavelengths. The geometry of the field, combined with the rotation of the star, determines the periodicity and intensity of observed signals. By analyzing these emissions, Astronomers reconstruct both surface and internal magnetic structures, correlating field strength with crustal composition and superfluid behavior. Throughout the neutron star, the balance of forces is delicate but robust. Gravity relentlessly pulls inward, while degeneracy pressure, nuclear interactions, and electromagnetic effects maintain equilibrium. The density gradient from the crust to the core ensures that matter adapts to local conditions, with each layer supporting those above and below it. Rotation and magnetic fields introduce additional structure, influencing how the star radiates energy and evolves over time. Observations across multiple wavelengths confirm the presence of these layers and their properties, creating a comprehensive picture that aligns with theoretical expectations. You notice that despite the extreme conditions, the neutron star is remarkably stable. Its radius and mass remain essentially constant over millennia, while internal processes adjust subtly, producing observable effects without destabilizing the star. Thermal evolution, magnetic decay, and rotational slowdown occur gradually, providing a slow rhythm that can be measured from afar. These changes are predictable and consistent with models based on known physics, reinforcing the connection between theory and observation. Finally, you reflect on how each layer contributes to the star's overall behavior. The crust mediates surface phenomena, the outer core supports superfluid and superconducting flows, and the inner core contains the densest matter in the universe. Together, they create a cohesive object whose properties can be inferred from careful measurement. Observations of pulsar timing, thermal emission, and gravitational effects all carry signatures of the internal structure, allowing you to trace the star's composition without directly penetrating it. As you observe the star in its stable configuration, its layers interwoven with extreme density, magnetic fields, and rotation, you begin to sense how these internal structures influence the energy and radiation that emerge. The way matter, pressure, and magnetic forces interact within the star sets the stage for the patterns of pulses and flares that will eventually reveal the secrets of its magnetic and rotational behavior. You focus on a neutron star that has settled into rotation, its magnetic field strong and organized. The field is tilted relative to the star's rotation axis, creating beams of electromagnetic radiation that sweep across space. As the star spins, these beams appear to pulse periodically to a distant observer, a phenomenon that gives pulsars their name. You follow the precise rhythm, noting that some pulsars complete hundreds of rotations per second, while others rotate more slowly, with periods of seconds. The beams of a pulsar are produced by charged particles accelerating along magnetic field lines. Near the magnetic poles, intense electric fields pull electrons from the surface, producing cascades of high-energy particles. These particles emit radiation in radio, X-ray, or gamma-ray frequencies, depending on their energy. The alignment of the magnetic axis and the rotation axis determines whether the beam intersects an observer's line of sight. Even slight misalignments produce a distinctive, periodic pulse. Observations of these pulses provide direct insight into the neutron star's rotation, magnetic field geometry, and surface conditions. You notice that the timing of pulses is extraordinarily precise. Some pulsars rival atomic clocks, with pulse periods predictable to within billionths of a second. This regularity allows astronomers to detect minuscule variations caused by interactions with companion stars, interstellar medium effects, or gravitational waves. Each deviation carries information about processes both near the pulsar and along the path of the radiation. The precision also allows tests of general relativity, such as the decay of orbital periods in binary systems, confirming theoretical predictions about energy loss through gravitational waves. The origin of the pulsar's magnetic field lies in the collapse of the progenitor star. As the stellar core shrank during the supernova, magnetic flux was conserved, amplifying the field to extraordinary strength. A typical pulsar has a surface field of around 1 trillion Gauss, sufficient to influence the motion of charged particles near the star. The field governs the acceleration of particles and the direction of emitted radiation. Over time, the field may decay, but during the early phases, it dominates the star's interaction with its surroundings. You trace the journey of the emitted radiation. As radio waves propagate through space, they interact with free electrons in the interstellar medium, experiencing dispersion that spreads the pulse in time. By measuring this effect, astronomers can estimate the distance to the pulsar and the density of electrons along the line of sight. These measurements are supported by observations of pulsars in globular clusters and the galactic plane, providing a detailed map of interstellar matter. X-ray and gamma-ray pulses provide complementary information about the most energetic processes near the magnetic poles. Pulsars also experience gradual changes in rotation. As they emit radiation, rotational energy is lost, causing the spin rate to decrease slowly. The rate of slowdown or spin-down depends on magnetic field strength and moment of inertia. By observing the change in pulse period over decades, astronomers calculate a pulsar's characteristic age and energy loss rate. Young pulsars spin rapidly and lose energy quickly, while older pulsars rotate more slowly. These long-term observations provide a timeline for understanding neutron star evolution and energy dissipation. You note that some pulsars exhibit sudden changes in rotation known as glitches. These events, brief but measurable, result from interactions between the crust and the superfluid interior. Neutron superfluid vortices, which carry angular momentum, can unpin from the crust, transferring spin to the outer layers and producing a sudden increase in rotation rate. The frequency and magnitude of glitches vary between pulsars, offering insight into the superfluid properties and crustal dynamics. Careful monitoring allows researchers to link observed behavior to theoretical models of dense matter physics. Binary pulsars offer additional complexity. When a neutron star orbits a companion, gravitational interactions can influence pulse timing and shape. Mass transfer from the companion can spin up the pulsar, creating a millisecond pulsar that rotates hundreds of times per second. The combination of rotation, mass, and magnetic field produces observable signals across the electromagnetic spectrum. Observing these systems allows measurement of neutron star masses, testing models of stellar evolution and dense matter. The Hulse-Taylor pulsar, for example, provided the first indirect detection of gravitational waves, validating Einstein's predictions. The electromagnetic radiation from pulsars is not uniform across all frequencies. Radio pulses often show substructure, microsecond-level variations, and changes in intensity. X-ray emissions can be pulsed due to hot spots on the surface created by returning charged particles. Gamma-ray pulses originate from regions further from the surface, where particle acceleration is strongest. Each type of observation informs a different aspect of the neutron star's structure and behavior. By combining data from multiple wavelengths, scientists construct a detailed picture of the magnetic field geometry, surface conditions, and particle interactions. You consider the impact of relativistic effects. Rapid rotation and strong gravity alter the observed signals. Time dilation, gravitational redshift, and light bending affect the apparent pulse period and shape. General relativity predicts these effects precisely, and pulsar observations confirm them. The bending of light near the surface allows radiation from regions normally hidden to be visible, providing information about the star's compactness. These relativistic influences are subtle but measurable, reinforcing the connection between observation and fundamental physics. Long-term monitoring of pulsars reveals gradual evolution in both rotation and emission properties. The decay of magnetic fields, combined with spin-down, changes the pulsar's visibility over millions of years. Some pulsars eventually cease to emit detectable radiation, becoming dead neutron stars. Others maintain sufficient magnetic energy to remain active. Observing a population of pulsars across different ages and spin rates allows astronomers to reconstruct the life cycle of neutron stars, correlating measured quantities with theoretical models. You observe the broader role of pulsars in astrophysics. Pulsar timing arrays detect tiny variations in pulse arrival times across multiple stars, searching for gravitational waves from supermassive black hole binaries. Pulsars in globular clusters map dense stellar environments. They even provide a probe of interstellar medium turbulence through the dispersion and scattering of radio waves. Each pulsar is a natural laboratory for testing extreme physics, from magnetohydrodynamics to quantum superfluidity, under conditions inaccessible on Earth. The precise and predictable rhythm of pulsars contrasts with the extreme conditions of their interiors. Superfluid neutrons, superconducting protons, and immense magnetic fields combine to produce the signals you observe. Each pulse carries encoded information about the star's mass, radius, rotation, magnetic field, and environment. By carefully analyzing this radiation, you trace the connection between internal structure, external emission, and the surrounding interstellar space. Finally, you reflect on how pulsars are both markers of stability and signs of dynamic processes. Their regular pulses are reassuringly consistent, yet subtle variations reveal complex physics within. The beams of radiation, sweeping across vast distances, provide a direct link to the extreme matter and forces within the star. As you follow their periodic rhythm, you begin to sense how these stable emissions interact with magnetic field evolution and energy loss mechanisms, hinting at the processes that distinguish ordinary pulsars from the most magnetically active neutron stars. You focus on a neutron star whose magnetic field is extraordinary trillions of times stronger than Earth's. These objects, known as Magnetars, are distinguished by their immense magnetic energy, which governs much of their behavior. Unlike ordinary pulsars, whose energy is largely derived from rotational kinetic energy, Magnetars are powered primarily by the decay of their magnetic fields. The surface field strength can reach up to a quadrillion Gauss, altering the motion of charged particles and creating intense electromagnetic emissions. The structure of the magnetic field is complex, with both dipolar and higher-order components. The field threads through the crust and extends into the surrounding magnetosphere. Charged particles within the star are constrained to follow field lines, producing currents that contribute to heating the crust. The energy stored in the magnetic field exceeds the total rotational energy, allowing magnetars to remain luminous even as their rotation slows. You observe that this decay produces gradual but significant changes in surface temperature and magnetic configuration over thousands to millions of years. Magnetic stresses build within the crust. The solid lattice of nuclei is stretched and twisted by the internal field. When the stress exceeds the structural strength of the crust, the material fractures, producing a starquake. These sudden rearrangements release bursts of energy, observed as X-ray or soft gamma-ray flares. The magnitude of these events can be immense, with some flares releasing more energy in a fraction of a second than the sun emits in a century. Observations of such bursts from magnetars in our galaxy confirm the connection between magnetic stress and high-energy emission. You note that the crust itself is extraordinarily dense, yet it is capable of supporting the weight of the overlying layers while accommodating magnetic stress. The interaction between the superfluid interior and the solid crust influences flare behavior. Currents in the magnetosphere respond to crustal shifts, producing rapid changes in radiation output. Satellites detect these signals with precise timing, allowing astronomers to reconstruct the dynamics of magnetic decay and crustal fractures. The repetition of such events in some magnetars demonstrates a gradual but persistent release of stored magnetic energy. Thermal evolution of magnetars differs from ordinary neutron stars. The decay of magnetic fields produces internal heating, maintaining surface temperatures higher than expected from age alone. X-ray observations show persistent thermal emission, often coupled with transient bursts. By measuring these emissions, astronomers estimate the strength and decay rate of the magnetic field. The cooling behavior provides insight into the composition of the crust and the efficiency of thermal conduction through dense matter. Superfluid layers within the core also transport heat differently from ordinary matter, influencing the observed surface temperature patterns. You observe the rotation of magnetars, generally slower than typical young pulsars. Their periods range from a few seconds to tens of seconds, reflecting the dominance of magnetic braking. The strong field exerts torque on the star, converting rotational energy into electromagnetic radiation. The rotational slowdown is measurable, providing data about the moment of inertia and magnetic field strength. Some magnetars show variations in rotation, small glitches, or timing noise, revealing interactions between the superfluid interior and magnetic stresses. Each variation is recorded precisely, offering a window into the star's internal physics. The magnetosphere is an active environment, where field lines trap particles and produce currents. The interaction of these particles with radiation results in complex emission patterns, including bursts, flares, and persistent X-ray output. Charged particles moving along twisted magnetic lines can emit synchrotron radiation or induce pair production, creating dense electron-positron plasmas. Observations of magnetar spectra and timing reveal the properties of these plasmas and the magnetic geometry, confirming theoretical models of field-driven energy release. Magnetars are sometimes observed to produce giant flares, extremely energetic events detectable even in other galaxies. These flares, which can briefly outshine the entire Milky Way in high-energy radiation, originate from catastrophic rearrangements of the magnetic field and crust. The timing and intensity of these flares provide constraints on the total magnetic energy stored and the stiffness of the crust. The repeatability of smaller bursts, combined with occasional giant flares, allows scientists to map how magnetic stress accumulates and is released over time. You consider how magnetars evolve. Initially formed as rapidly rotating neutron stars, they spin down quickly due to strong magnetic torques. The decay of the magnetic field releases energy gradually, producing a luminous X-ray source long after rotational energy diminishes. Over tens of thousands to hundreds of thousands of years, the field weakens, and the star may eventually resemble a more ordinary pulsar. Observational surveys of magnetars across different ages confirm this evolutionary trend, linking field strength, rotation, and emission properties. Interactions with surrounding space are also notable. The intense magnetic field can influence the motion of particles in the nearby interstellar medium, accelerating cosmic rays and shaping nebular structures. Persistent X-ray emission and flare activity contribute energy to the local environment. In some cases, magnetars are found near supernova remnants, connecting their birth in core collapse events to observed high-energy phenomena. Measurements of surrounding gas, radiation, and particle flux help scientists understand the broader astrophysical impact of these objects. Relativistic effects are measurable in magnetars as well. Light emitted near the surface is gravitationally redshifted due to extreme curvature of spacetime. Rotation and strong magnetic fields modify the propagation of photons, producing polarization and spectral features that can be detected by sensitive instruments. These observations allow determination of mass-to-radius ratios, surface magnetic geometry, and the properties of the magnetized crust. By combining data from multiple wavelengths and instruments, astrophysicists reconstruct the physical environment of magnetars in remarkable detail. You notice that despite the intensity of their fields and emissions, magnetars remain stable objects over long timescales. Magnetic decay, starquakes, and rotational slowdown are gradual processes. Observations spanning decades confirm that energy is released systematically, consistent with theoretical models. The extreme conditions within a magnetar provide natural laboratories for studying physics inaccessible on Earth, including behavior of matter at supernuclear densities and the limits of magnetic stress on solid lattices. Finally, you reflect on the contrast between magnetars and ordinary pulsars. Both are neutron stars, yet their dominant energy source differs: rotation versus magnetic decay. Their emission patterns, rotational periods, and interaction with surroundings reflect these differences. Observing magnetars deepens understanding of how neutron stars can vary widely despite similar origins. As the magnetic field evolves, producing bursts, flares, and persistent radiation, you begin to sense how this energy shapes the star's environment and sets the stage for the detailed study of rotational and magnetic interactions that follow in other neutron stars. You focus on a neutron star in steady rotation, observing the interplay between spin and magnetic field. The star's rotational energy is enormous, stored in the motion of a mass greater than the Sun compressed into a sphere barely 10 kilometers wide. This energy powers emissions, influences the star's structure, and drives interactions with its surroundings. As the star rotates, its magnetic field channels particles along field lines, producing radiation that emerges from the magnetic poles. The rotation of the star transforms this radiation into the periodic pulses detected as pulsar signals. Rotational energy decreases gradually as the star emits radiation and particles. This energy loss, called spin down, is measurable through long-term observations of pulse timing. The rate at which the period increases depends on both the magnetic field strength and the moment of inertia. Young neutron stars spin rapidly and lose rotational energy more quickly, while older stars rotate more slowly. By calculating the spin-down rate, astronomers estimate the characteristic age of the star and the total energy radiated over time. This precise connection between observation and physical parameters provides a reliable method for understanding neutron star evolution. Magnetic fields exert torque on the star, converting rotational energy into electromagnetic radiation. The strength of the field determines how efficiently energy is extracted. Ordinary pulsars have fields around 1 trillion Gauss, while magnetars may reach 1 quadrillion. In both cases, the interaction between the magnetic field and charged particles in the magnetosphere produces radiation that carries away angular momentum. The loss of angular momentum manifests as a gradual increase in the rotational period, a phenomenon observable with exceptional precision thanks to pulsar timing. You observe that the emitted radiation spans a wide range of frequencies. Radio pulses arise from coherent emission mechanisms involving electrons accelerated along magnetic field lines. X-rays originate from hot spots on the neutron star's surface, often near the magnetic poles, created by returning charged particles. Gamma rays are produced in regions further from the surface where particle acceleration is strongest. Each component provides a different window into the star's physics: the surface, the magnetosphere, and the interaction between fields and plasma. Multi-wavelength observations enable scientists to reconstruct the energy budget and emission geometry of the neutron star. Spin and magnetic field interact in complex ways. Rapid rotation can amplify particle acceleration, while magnetic stresses modify the flow of currents in the magnetosphere. Some pulsars experience sudden changes in rotation known as glitches, caused by interactions between the superfluid interior and the solid crust. When angular momentum is transferred from the superfluid to the crust, the rotational period briefly decreases. Monitoring these glitches allows astrophysicists to probe the properties of superfluid matter and the coupling between interior layers, connecting microscopic quantum behavior to observable macroscopic effects. Energy loss through radiation is not uniform. The efficiency of energy conversion depends on the star's spin rate, magnetic field, and particle density in the magnetosphere. Young pulsars with strong fields emit more energetically, producing bright X-ray or gamma-ray pulses. Older pulsars with weaker fields radiate less but remain detectable in radio frequencies. Long-term observations reveal how energy output evolves over time, correlating with spin-down and magnetic field decay. The balance of forces ensures the star remains structurally stable despite continuous energy loss. You note that the rotational kinetic energy of a neutron star can be comparable to the energy released in a supernova. For millisecond pulsars, the rapid spin contains tremendous energy, extracted gradually to power emission and particle acceleration. The energy manifests as pulses, particle winds, and, in some cases, heating of surrounding gas. Observing pulsar wind nebulae provides direct evidence of how rotational energy is transformed into radiation and kinetic energy, shaping the star's environment and influencing nearby interstellar matter. Magnetic braking plays a central role in rotational evolution. The torque exerted by the magnetic field slows the spin, converting rotational energy into electromagnetic radiation. The braking index, derived from the spin-down rate and its derivatives, measures how rotation evolves under magnetic and radiative forces. Observed values often differ slightly from theoretical predictions, indicating additional processes such as particle winds or changes in the magnetic field configuration. These observations refine models of neutron star energy loss and long-term evolution. Particle acceleration within the magnetosphere produces additional observable effects. Electrons and positrons accelerated along magnetic field lines emit synchrotron radiation and curvature radiation. These mechanisms account for emissions in radio, X-ray, and gamma-ray frequencies. The radiation is highly directional, contributing to the pulsed signal detected by distant observers. Observations of pulse shape, intensity, and polarization provide insight into the magnetic field geometry and the spatial distribution of accelerated particles. Combining these data with spin measurements offers a comprehensive understanding of the star's energy dynamics. Thermal energy also plays a role in the neutron star's overall radiation. Heat from the interior emerges through the crust and surface, contributing to X-ray emission. In young neutron stars, residual thermal energy from formation is significant, but it gradually diminishes as the star cools over thousands of years. Magnetic field decay in magnetars provides additional heating, maintaining elevated surface temperatures. Observations of surface temperature, combined with knowledge of rotation and magnetic field, allow scientists to infer internal properties such as thermal conductivity, superfluidity, and crust composition. You notice that the combination of spin, magnetic field, and particle acceleration establishes a self-regulating system. Faster rotation produces more energetic emission, while slower rotation reduces output. Magnetic field decay gradually alters emission patterns, particularly in magnetars. The star remains stable, balancing centrifugal force, degeneracy pressure, and magnetic stresses. Observations across the electromagnetic spectrum provide evidence of this balance, demonstrating the intimate connection between fundamental forces and measurable phenomena. Long-term monitoring of pulsars shows predictable evolution in spin and energy output. Millisecond pulsars, spun up by accretion from companion stars, can rotate hundreds of times per second, producing intense beams of radiation. Ordinary pulsars gradually slow down, their spin periods lengthening over millions of years. The combination of rotational energy, magnetic braking, and particle acceleration explains the variety of observed neutron star behaviors, from bright young pulsars to slowly rotating older stars with weaker emission. Finally, you reflect on the continuous interplay between rotation and radiation. The star's spin powers the beams, while magnetic fields govern how energy is released. Each pulse carries encoded information about the star's structure, internal dynamics, and interaction with surrounding space. As the neutron star emits radiation, you begin to sense how these processes connect with magnetic field evolution, starquakes, and high-energy flares, hinting at the phenomena that distinguish the most magnetically active neutron stars. You begin by considering how neutron stars, despite their small size, can be detected across vast distances. Their compactness and extreme energy output make them observable through multiple channels, primarily electromagnetic radiation. Pulsars emit periodic radio waves that sweep across the sky, producing a lighthouse-like signal detectable with sensitive radio telescopes. Radio observatories measure the arrival times of pulses with extraordinary precision, revealing the rotation period of the star and variations caused by its environment. The radio signal carries additional information beyond rotation. Dispersion occurs as pulses travel through the interstellar medium, causing lower frequency waves to arrive later than higher frequency waves. Measuring this dispersion allows astronomers to estimate the electron density along the line of sight and the distance to the pulsar. These measurements help map the structure of our galaxy, while also confirming that the observed timing variations are consistent with theoretical models of pulse propagation through space. X-ray observations provide complementary insight. Thermal emission from the neutron star's surface, often concentrated in hot spots near the magnetic poles, is observable with space-based X-ray telescopes. Young neutron stars retain significant residual heat from their formation, while magnetars are further heated by magnetic field decay. Measuring surface temperature and spectrum allows scientists to infer the thermal conductivity of the crust, the presence of superfluid layers, and the structure of the magnetic field near the surface. X-ray bursts also indicate dynamic processes such as starquakes or magnetospheric reconnection events. High-energy gamma-ray observations reveal the most energetic processes in and around neutron stars. Particles accelerated along magnetic field lines emit curvature radiation and synchrotron radiation, which produce pulsed gamma rays detectable with specialized space telescopes. These observations complement radio and X-ray data, providing a more complete view of particle acceleration, field geometry, and energy distribution. By combining measurements across wavelengths, astronomers reconstruct the emission mechanisms and map the magnetosphere. Optical and infrared detection is rare but possible in nearby neutron stars. Thermal emission at lower energies may be observed from young pulsars or magnetars with sensitive instruments. Studying these signals contributes to understanding the star's cooling rate and surface composition. Spectral lines, though weak, offer clues about the composition of the outermost layers, and the presence of atmospheric elements or fallback material from the supernova. Each wavelength band provides a unique window into the physical conditions of the star. Timing observations remain the most precise tool for studying neutron stars. Radio pulses are monitored over years and decades, revealing gradual spin-down, glitches, and other subtle variations. Binary systems provide additional data. Orbital motion induces changes in pulse arrival times, allowing measurement of the neutron star's mass and the dynamics of the system. Observations of these effects have been used to test general relativity, including the detection of energy loss due to gravitational waves in compact binaries. You observe that pulsar timing can detect minute influences on the star's motion. Interactions with companion stars, accretion disks, or planetary systems produce measurable variations in pulse arrival times. Multi-decade monitoring enables detection of tiny changes, revealing both intrinsic properties and external influences. Timing arrays, which compare signals from multiple pulsars, are used to search for low-frequency gravitational waves, demonstrating how neutron star observations extend beyond individual systems to broader cosmic phenomena. Radio interferometry provides spatial resolution of pulsar wind, nebulae, and surrounding supernova remnants. By combining signals from multiple antennas, astronomers create detailed maps of the environment around neutron stars. These observations reveal how particle winds, magnetic fields, and high-energy radiation shape surrounding gas, producing emission structures observable in radio, X-ray, and optical wavelengths. Studying these nebulae confirms energy output models and shows how rotational or magnetic energy interacts with the interstellar medium. Magnetic field measurements are inferred from spin-down rates and X-ray spectra. The strength of the dipole component determines how rapidly a star slows its rotation. Observed timing properties, combined with theoretical models, allow calculation of field strength and distribution. For magnetars, the analysis of X-ray bursts and surface thermal emission provides further constraints on magnetic decay, field geometry, and crustal stress. These observational techniques confirm predictions from nuclear physics and magnetohydrodynamics applied under extreme conditions. You also notice that neutron star mass and radius are determined through multiple observational approaches. In binary systems, orbital dynamics yield precise mass measurements. X-ray spectroscopy of surface emission or accretion hotspots allows inference of radius, particularly when gravitational redshift is considered. Observations of thermonuclear bursts from accreting neutron stars provide additional constraints. Combining these measurements enables testing of the equation of state for ultradense matter, a fundamental property determining internal structure, density distribution, and maximum stable mass. Neutrino detection, while limited to nearby supernovae, provides direct evidence of the core collapse process that produces neutron stars. Neutrino bursts precede optical detection and reveal the dynamics of core collapse, neutronization, and energy transport during the formation phase. Observing these events confirms theoretical models of supernova physics and supports our understanding of neutron star birth conditions. Neutrino observatories continue to improve, offering the potential for more detailed insights in the future. Gravitational wave astronomy is now contributing to neutron star observations. Merging binary neutron stars produce measurable ripples in spacetime, providing mass, radius, and tidal deformability data. These measurements complement electromagnetic observations and provide independent constraints on the equation of state. By combining data from gravitational waves and electromagnetic signals, astrophysicists gain a more complete understanding of neutron star physics and the extreme conditions in which they exist. You note that multi-wavelength and multi-messenger observations are essential for understanding neutron stars. No single type of measurement captures all relevant physical information. Radio, X-ray, gamma ray, optical, neutrino, and gravitational wave data provide complementary perspectives. By analyzing these signals together, scientists reconstruct internal structure, magnetic field configuration, rotation, energy output, and evolutionary history. Observations of neutron stars confirm that theory and measurement align under extreme physical conditions, offering a window into some of the densest matter in the universe. Finally, you reflect on the precision and depth of neutron star observations. Each pulse, flare, or thermal emission carries information about the star's interior, magnetic field, and surroundings. Long-term monitoring and cross-disciplinary studies provide a detailed understanding of these compact objects. As you follow the radiation patterns, timing variations, and multi-wavelength signals, you begin to sense how observational techniques connect with fundamental physics, revealing the complex interplay between gravity, magnetism, rotation, and high-energy particle dynamics. You observe a neutron star whose magnetic field is immense, threading through the crust and the core. Over thousands to millions of years, this field does not remain static. It changes gradually due to processes that govern the flow of currents in the dense interior. One of the primary mechanisms is ohmic decay, the gradual dissipation of electric currents due to the finite electrical conductivity of the star's crust. Even though the crust is highly conductive, the extreme density allows small resistances to accumulate, converting magnetic energy into heat. This process is slow but measurable and contributes to the gradual weakening of magnetic fields in ordinary pulsars. Hall drift operates alongside ohmic decay, particularly in the outer crust. It involves the motion of magnetic field lines caused by interactions between electrons and the solid lattice of nuclei. Unlike ohmic decay, which directly dissipates energy, Hall drift redistributes magnetic energy within the crust. This process can concentrate magnetic flux into localized regions, producing intense surface fields that influence bursts, hotspots, and emission patterns. Observations of magnetic hotspots on pulsar and magnetar surfaces support the role of Hall drift in shaping field geometry over time. Deeper inside the neutron star, the core may contain superconducting protons. In a Type II superconducting state, magnetic flux is confined to quantized tubes, which interact with the surrounding superfluid neutrons. The motion of these flux tubes determines how the core field evolves. Flux tubes can pin to the superfluid vortices that carry rotational angular momentum, linking magnetic evolution to changes in spin. The interactions between flux tubes and vortices also influence starquake activity and glitch behavior, connecting interior physics to observed phenomena. You notice that the rate of field decay depends on multiple factors. Stronger initial fields, higher crustal temperatures, and the density structure all affect how rapidly magnetic energy diminishes. In magnetars, the initial field may be so strong that even with decay, the star remains extraordinarily magnetic for tens of thousands of years. In ordinary pulsars, weaker initial fields combined with ohmic dissipation and slower Hall drift lead to gradual weakening over millions of years. Observational surveys of pulsar populations confirm these trends, showing a distribution of field strengths and ages consistent with theoretical predictions. The interaction between magnetic field evolution and rotation is subtle but important. As magnetic fields decay, the torque applied to the neutron star diminishes, slightly altering the spin-down rate. In young magnetars, rapid field decay generates internal heating, maintaining elevated surface temperatures that are observable in X-rays. In older, weaker field neutron stars, slower decay contributes less thermal energy, producing cooler surfaces. Comparing surface temperature measurements with magnetic field estimates provides evidence for these internal processes. You observe how crustal composition influences field evolution. The presence of heavy nuclei, electron density, and lattice structure affects both electrical conductivity and the Hall effect. Crustal impurities can enhance resistive dissipation, accelerating ohmic decay. Conversely, a more uniform lattice preserves current flow for longer, slowing decay. Observations of thermal emission from neutron stars allow indirect inference of crustal properties, showing consistency between measured cooling rates and predicted field decay timescales. Magnetospheric currents also play a role in magnetic evolution. The movement of charged particles in the magnetosphere interacts with surface fields, inducing additional stresses and currents within the crust. Over time, this feedback loop subtly modifies the magnetic configuration. Observations of variable emission patterns, pulse profiles, and timing noise in pulsars provide evidence of such magnetospheric influence. These variations, while small compared to the total field, contribute to the complex evolution of the star's observable properties. In the deepest layers of the core, superconducting protons restrict the motion of magnetic flux, stabilizing the field over longer timescales. The quantized flux tubes, if tightly coupled to the superfluid vortices, resist rapid rearrangement. However, slow migration of flux lines through the core allows gradual adjustment, which can ultimately influence surface field strength. These internal mechanisms are difficult to observe directly, but comparisons of pulsar and magnetar evolution across populations support the presence of stable superconducting cores in many neutron stars. Field evolution is not always monotonic. Hall drift can temporarily concentrate flux, producing localized high-field regions even as the global field decays. These regions may produce enhanced emission, bursts, or surface heating. Observationally, some magnetars show persistent hotspots or periodic flare activity consistent with localized magnetic stresses. Such evidence confirms that field evolution is dynamic, with competing processes of decay, redistribution, and internal migration. You also notice that interactions with companion stars in binary systems can influence field evolution. Accretion of material deposits fresh plasma onto the crust, potentially burying the magnetic field and reducing its observable strength. Over time, the field may reemerge through buoyancy or diffusion, a process supported by observations of recycled millisecond pulsars. These systems demonstrate that magnetic evolution is not purely internal, but can be influenced by external factors, providing a broader perspective on neutron star life cycles. Thermal evolution is closely linked to magnetic decay. Ohmic dissipation and Hall drift convert magnetic energy into heat, warming the crust and surface. This heating slows cooling, particularly in strongly magnetized neutron stars. By measuring surface temperature and luminosity, astronomers infer both the magnetic field strength and the rate of decay. Observations of magnetars show elevated X-ray luminosity consistent with ongoing magnetic heating, while ordinary pulsars cool more efficiently, reflecting slower or weaker decay processes. You consider the observational evidence that supports these theories. Surveys of pulsar populations reveal correlations between age, spin-down rate, surface temperature, and field strength. Younger neutron stars often exhibit stronger fields and higher thermal emission, while older stars show weaker fields and cooler surfaces. Magnetars occupy a distinct region of this parameter space, confirming the impact of initial conditions and subsequent magnetic evolution. Timing observations, thermal measurements, and spectral analysis collectively validate theoretical models. Finally, you reflect on the interplay between magnetic evolution and neutron star diversity. The processes of ohmic decay, Hall drift, and superconducting core dynamics explain why some stars remain magnetically active as magnetars, while others evolve into ordinary pulsars. Each neutron star follows a unique evolutionary path determined by initial mass, rotation, magnetic field configuration, and environmental factors. Observations across decades, combined with theoretical modeling, provide a coherent picture of how magnetic fields shape the life and behavior of neutron stars. As you follow the gradual transformation of magnetic fields, the slow redistribution of currents, and the subtle interaction between crust, core, and magnetosphere, you begin to sense how these changes influence bursts, spin, and radiation, linking internal evolution to the dynamic phenomena observable across the galaxy. You observe a neutron star whose magnetic field exerts tremendous stress on its solid crust. The crust, composed of nuclei arranged in a dense lattice, is rigid but not infinitely strong. As the magnetic field evolves, currents flowing through the crust create additional stress, gradually deforming the lattice. Over time, the pressure accumulates, and when the stress exceeds the structural strength of the crust, the material fractures in an event known as a starquake. These quakes release energy abruptly, detectable as sudden changes in rotation or bursts of electromagnetic radiation. Starquakes are analogous in a precise sense to earthquakes on Earth but far more extreme. The crust is orders of magnitude denser, and the energy released in a typical quake can exceed the sun's daily output. The rearrangement of matter affects not only the crust but also the star's magnetic field configuration. As the solid lattice shifts, magnetic field lines anchored to the crust are displaced, producing rapid adjustments in the magnetosphere. These movements accelerate charged particles, resulting in bursts of X-rays or gamma rays observable across the galaxy. You note that the energy released depends on the size of the fracture and the strength of the local magnetic field. In magnetars, where surface fields may exceed a quadrillion Gauss, Even small crustal shifts can produce intense flares. Observations have recorded giant flares releasing more energy in a fraction of a second than the sun emits over a century. Less energetic quakes produce smaller bursts or subtle changes in pulse timing, providing a spectrum of observable phenomena connected to internal stress and fracture dynamics. The structure of the crust influences how energy is transmitted. The outer layers consist of tightly packed nuclei and a degenerate electron gas, creating a lattice capable of supporting stress while remaining brittle. Fractures propagate along planes of weakness, and the size and orientation of these fractures determine the distribution of released energy. Seismic waves generated by the quake travel through the crust and can couple with the core, producing vibrations in the superfluid interior. These vibrations, though largely confined, may influence rotational behavior and magnetospheric currents. Magnetospheric interactions amplify the effect of starquakes. When magnetic field lines anchored in the crust shift suddenly, currents in the surrounding plasma are disrupted. The rapid rearrangement induces particle acceleration, producing bursts of high-energy radiation. The radiation often originates from regions near the magnetic poles, where field lines are most tightly curved. Satellites detect these signals as brief, intense flashes, confirming the connection between crustal stress, magnetic reconnection, and observable emission. You notice that glitches often accompany starquakes. These are sudden changes in rotational period, typically increases, caused by the transfer of angular momentum from the superfluid interior to the crust. The quake perturbs the coupling between vortices in the superfluid and the lattice, allowing previously pinned vortices to move. The redistribution of angular momentum produces a measurable change in rotation, which can be detected with precise timing observations. Glitches provide a direct window into the interplay between crustal mechanics and superfluid physics. The timing and frequency of starquakes depend on multiple factors, including magnetic field strength, crustal composition, and age. Younger magnetars with stronger fields and more elastic crusts experience more frequent and energetic quakes. Older neutron stars with weaker fields and cooler crusts exhibit less dramatic events. Observations of magnetar populations show correlations between age, field strength, and burst activity, supporting models that link magnetic stress and crustal mechanics to observable flare behavior. You explore the connection between magnetic field decay and flare frequency. As the field slowly dissipates, stress builds in localized regions of the crust. Hall drift can concentrate magnetic flux, increasing local stress and making fractures more likely. The interplay of ohmic decay, crustal rigidity, and flux redistribution determines the timing and intensity of flares. This dynamic system explains the variety of burst energies observed, from small, frequent events to rare giant flares. Thermal effects also contribute to flare activity. Ohmic dissipation in the crust generates heat, altering material properties and potentially weakening regions under stress. Elevated temperature increases plasticity in certain layers, changing how fractures propagate. Thermal measurements from X-ray satellites reveal correlations between hotspots, flare regions, and crustal heating, confirming that the internal energy distribution affects observable events. You consider the geometry of starquake-induced emissions. Magnetic poles are often the focal points of high-energy bursts because field lines converge there, channeling accelerated particles. The beam of radiation is directional, producing observable pulses or flashes depending on orientation relative to Earth. Careful monitoring of flare profiles and repetition patterns allows astronomers to map magnetic field structures and infer the locations of stress accumulation within the crust. These observations connect internal physics to external signals with remarkable precision. Observing multiple starquakes over time reveals patterns in energy release. Some magnetars exhibit repeated bursts from the same region, suggesting persistent magnetic stress concentrations. Other stars produce isolated flares, indicating that stress is redistributed differently in each object. By comparing events across neutron stars, scientists develop statistical models that predict flare frequency and intensity based on field strength, rotation, and crustal composition. These models align closely with decades of observational data. You note that starquakes can influence surrounding space. Bursts of X-rays and gamma rays deposit energy into the magnetosphere, accelerating particles and producing transient plasma structures. In extreme cases, flares can interact with nearby interstellar gas, generating observable nebular changes. The energy released in flares also contributes to long-term magnetic field evolution, gradually adjusting the distribution of currents and magnetic flux in the crust and outer layers. Observations confirm these connections, linking small-scale internal events to larger-scale astrophysical phenomena. Finally, you reflect on the delicate balance within neutron stars. The crust supports immense magnetic stress, but even small adjustments can release significant energy. Starquakes reveal the coupling between the rigid crust, the superfluid interior, and the magnetosphere, providing insight into fundamental physics under extreme conditions. Observations of X-ray and gamma-ray bursts, combined with timing data, allow you to follow these processes in real time. As you follow the sequence of flares and glitches, you begin to sense how interactions with companion stars, accretion, and energy loss mechanisms influence neutron star behavior, gently leading toward the dynamics of binary systems. You follow a neutron star in a close binary system, orbiting a companion star. The gravitational field of the dense neutron star exerts strong tidal forces on the companion, pulling material from its outer layers. When the companion evolves and fills its Roche lobe, matter flows through the inner Lagrange point, forming a stream that spirals toward the neutron star. Angular momentum prevents the material from falling directly onto the surface, creating an accretion disk in which viscous forces gradually transport matter inward. The accretion process converts gravitational potential energy into kinetic and thermal energy. As material spirals inward through the disk, friction and magnetic interactions heat it to millions of kelvins, producing X-ray emission detectable by space-based telescopes. Observations of X-ray luminosity provide a direct measure of the mass accretion rate. Bright X-ray pulsars are often the result of high accretion rates, where hotspots form near the magnetic poles as inflowing material is guided along field lines and collides with the surface. The neutron star's magnetic field shapes the flow of accreted matter. Material reaching the magnetosphere is channeled along field lines toward the magnetic poles, forming localized regions of impact known as accretion columns. The kinetic energy of infalling matter is converted into heat and radiation, creating X-ray hotspots with characteristic pulsations. The pulse period corresponds to the star's rotation, allowing precise measurement of spin. Variations in pulse profile and intensity provide insight into field geometry, accretion dynamics, and disk structure. Accretion alters the rotational dynamics of the neutron star. The inflowing material transfers angular momentum, spinning the star up over time. Millisecond pulsars are thought to originate from this process, having been recycled through sustained accretion from a companion. Observations confirm gradual shortening of spin periods in accreting systems, demonstrating the direct influence of angular momentum transfer. In some systems, sudden changes in spin, known as torque reversals, occur when the balance between magnetic braking and accretion shifts, providing measurable evidence of the complex interplay between rotation and accretion. You observe that the magnetic field may also evolve due to accretion. Inflowing plasma can bury surface magnetic flux, reducing the observable field strength over time. The suppression of the magnetic dipole affects the spin-down rate and emission properties. Over long timescales, the field can re-emerge through diffusion or buoyancy, restoring some surface strength. Observational data from accreting millisecond pulsars show weaker fields compared to young isolated pulsars, supporting the role of accretion in modifying magnetic properties. Thermal emission from the surface provides additional observational clues. The impact of accreted matter creates localized hotspots whose temperature can exceed 10 million kelvins. X-ray spectroscopy resolves these hotspots, measuring temperature, size, and flux. Observed variability in brightness and spectral hardness traces changes in accretion rate and column geometry. Repeated observations confirm that hotspot characteristics are closely linked to both rotation and magnetic channeling, offering a direct window into surface physics under extreme conditions. You consider the interaction between the disk and the neutron star's magnetosphere. The inner edge of the disk is truncated where magnetic pressure balances the ram pressure of accreting matter. This boundary determines the radius at which material is forced to follow magnetic field lines. Variations in accretion rate shift this radius, producing observable changes in pulse period and luminosity. Detailed measurements of quasiperiodic oscillations in X-ray flux provide constraints on the inner disk radius, neutron star mass, and magnetic field strength. In high-mass X-ray binaries, the companion stellar wind can contribute to accretion. The neutron star captures a fraction of the outflowing wind, producing variable X-ray emission. Observations show that fluctuations in wind density directly influence luminosity and spin torque, demonstrating how environmental conditions regulate the neutron star's energy output. In low-mass X-ray binaries, Roche lobe overflow dominates, producing more stable accretion disks. Comparative studies of these systems reveal consistent correlations between companion type, accretion mechanism, and observed radiation patterns. Glitches and spin variations in accreting systems are influenced by the interaction between the crust and superfluid interior. Material deposited on the surface exerts additional stress, which can perturb vortices in the superfluid. Sudden unpinning of vortices during torque changes or accretion bursts produces measurable changes in rotation, connecting observed timing anomalies to interior physics. Observations across multiple systems confirm that glitches in accreting pulsars differ from those in isolated stars, reflecting the combined influence of mass transfer and internal dynamics. Type 1 X-ray bursts occur in systems where accreted material builds up on the surface, triggering thermonuclear fusion. Hydrogen and helium accumulate until temperature and pressure conditions ignite runaway nuclear reactions, producing short, intense flashes of X-rays. These bursts reveal surface composition, accretion rate, and nuclear burning physics. Observations allow astrophysicists to measure neutron star mass and radius indirectly, using the burst luminosity and gravitational redshift, providing insight into fundamental properties under extreme conditions. You note that accretion also drives long-term evolution of neutron star systems. Sustained mass transfer can increase spin, modify the magnetic field, and alter emission patterns. Observations of recycled millisecond pulsars confirm this evolutionary path, linking X-ray binaries to the population of rapidly rotating, weakly magnetized neutron stars observed today. The transformation demonstrates the interconnected nature of rotation, magnetic field, and accretion, grounded in measured phenomena rather than speculation. Interactions between accretion disks and the surrounding space produce observable nebular features. Jets and outflows, formed by magnetic interactions in the inner disk, transport energy and angular momentum away from the system. Observations of these jets in X-ray and radio wavelengths show collimated structures, confirming theoretical models of disk magnetosphere coupling. The combined energy output of radiation, particle acceleration, and mass ejection shapes the environment, illustrating the broader astrophysical impact of accreting neutron stars. Finally, you reflect on the precision with which observations reveal the physics of accreting systems. Pulse timing, spectral analysis, burst measurements, and disk imaging together provide a comprehensive picture of mass transfer, rotational dynamics, magnetic evolution, and surface phenomena. Each accreting neutron star offers a laboratory for testing fundamental physics under extreme gravity, density, and magnetic conditions. As you follow these interactions, you begin to sense how energy loss, spin evolution, and magnetic stresses connect to the broader universe, gently leading toward the detection of gravitational waves and the ripples they create in spacetime. You focus on the subtle ripples in spacetime produced by neutron stars. According to general relativity, massive objects accelerating asymmetrically create gravitational waves, disturbances that propagate at the speed of light. Neutron stars, with their extreme density and rapid rotation, are efficient sources under certain conditions. Even slight deviations from perfect spherical symmetry, such as mountain-like deformations on the crust or uneven mass distribution, generate waves. These signals, though weak by the time they reach Earth, carry precise information about the star's mass, radius, and internal structure. Rotating neutron stars with small asymmetries produce continuous gravitational waves. The amplitude of these waves depends on the ellipticity, or deviation from perfect symmetry, of the star. Crustal stresses, magnetic field deformation, or frozen in mountains only a few centimeters high can produce detectable signals from nearby stars. Observatories such as LIGO and Virgo use laser interferometry to detect these minuscule changes in distance, smaller than the width of a proton, providing a direct measurement of spacetime perturbations caused by neutron star rotation. Binary neutron star systems are especially significant sources. As two compact stars orbit each other, they accelerate and lose energy in the form of gravitational waves. The orbital period decreases gradually, producing a predictable chirp signal in the detectors. Observations of such spirals confirm the predictions of general relativity and provide precise measurements of the masses and orbital parameters of the stars. The waveform shape encodes information about tidal deformability, indicating how the neutron star material responds to gravitational forces. You notice that gravitational wave detection also complements electromagnetic observations. When a binary neutron star merger occurs, the event may produce gamma-ray bursts, X-ray afterglows, and optical or infrared kilonovae. Correlating gravitational wave signals with these electromagnetic counterparts allows measurement of distances and testing of cosmological models. The simultaneous observation of multiple signals provides a multi-messenger perspective, revealing both the dynamics of the merger and the properties of the individual neutron stars. Continuous waves from isolated pulsars offer another method for studying neutron stars. By analyzing the periodicity of detected signals, astronomers can infer rotational parameters and ellipticity. Even small deviations in amplitude or frequency over time reflect structural changes, such as crustal relaxation or magnetic field evolution. Long-term monitoring improves sensitivity and constrains models of neutron star matter, including the rigidity of the crust and the behavior of the superfluid interior. Gravitational wave measurements reveal the neutron star equation of state. The tidal deformation of stars during mergers depends on the pressure-density relationship of ultradense matter. Comparing observed waveforms with theoretical models allows constraints on radius and compressibility. These constraints are invaluable, providing insight into the physics of matter at densities exceeding nuclear saturation, which cannot be replicated in terrestrial laboratories. Observational data thus directly informs fundamental nuclear physics. You observe that asymmetries in the crust or core enhance gravitational wave emission. Magnetic field stresses or temperature gradients can produce small deformations that increase ellipticity. Observations of millisecond pulsars, some with extremely stable rotation, place upper limits on these asymmetries. Such limits inform models of crustal composition and magnetic field distribution. The interplay between electromagnetic and gravitational signals reveals a consistent picture of neutron star structure under extreme conditions. Mergers of neutron stars generate short-lived but intense gravitational wave signals. During the final inspiral and collision, the star's dense cores experience tidal forces, oscillations, and mass ejection. Numerical simulations of general relativity and hydrodynamics predict waveform features, which are compared with detected signals to extract physical parameters. Observations of events such as GW 170817 have confirmed these models, allowing measurement of combined mass, mass ratio, and tidal deformability, as well as insights into the formation of heavy elements through our process nucleosynthesis. You notice that gravitational waves also carry information about the spin of neutron stars. Rotational deformation alters the waveform during binary inspiral, revealing alignment and magnitude of angular momentum. This information constrains evolutionary history, including whether the stars were spun up by accretion or formed in isolation. Gravitational wave astronomy thus provides a direct link between rotation, internal structure, and binary dynamics, extending understanding beyond what electromagnetic observations alone can achieve. Detectors like LIGO and Virgo measure strain by monitoring changes in the relative lengths of perpendicular arms using laser interferometry. Tiny variations caused by passing waves produce interference patterns, from which wave amplitude and frequency are extracted. Data processing removes noise from seismic, thermal, and instrumental sources, isolating the astrophysical signal. Multiple detectors operating simultaneously allow localization of the source in the sky, improving correlation with electromagnetic observations and increasing confidence in detection. You consider the significance of these observations for testing fundamental physics. Gravitational wave signals confirm that spacetime propagates disturbances at the speed of light and follows the predictions of general relativity even under extreme conditions. Observed waveforms provide stringent tests of alternative gravity theories. The consistency of multiple detections with relativistic predictions reinforces confidence in both theoretical frameworks and observational techniques. Tidal effects during mergers reveal information about internal structure. Neutron stars are not rigid spheres. The cores and crust deform under mutual gravity. The phase evolution of gravitational waves carries these signatures, allowing extraction of tidal deformability parameters. Such measurements constrain models of dense matter and nuclear interactions, offering a rare empirical test of physics at supernuclear densities. Observational data from multiple events continues to refine these constraints, reducing uncertainty in the properties of neutron star interiors. Finally, you reflect on the complementary nature of gravitational wave and electromagnetic observations. Waves reveal mass, spin, and deformability, while photons provide surface temperature, magnetic field, and radiation characteristics. Together, these signals allow a more complete understanding of neutron star structure, evolution, and extreme physics. Following these waves from distant mergers or continuous rotation, you sense how the behavior of matter and spacetime is intertwined, hinting at the ultimate fate of stars and the physics that governs the densest objects in the universe. You begin by observing a freshly formed neutron star, rotating rapidly with an immense magnetic field. The star emits beams of radiation from its magnetic poles, observed as pulsations when aligned with your line of sight. Over time, the rotation gradually slows as the star loses energy through electromagnetic radiation and particle winds. This spin-down process is measurable with precise timing of pulse arrivals, revealing a steady decrease in rotational frequency. By monitoring pulsars over decades, astronomers quantify the rate of energy loss, confirming theoretical predictions of magnetic dipole radiation. The magnetic field also evolves as the neutron star ages. In magnetars, the field remains exceptionally strong, producing bursts and heating the crust. In ordinary pulsars, the field weakens over millions of years through ohmic decay, Hall drift, and interactions with superfluid vortices. Observations of pulsar populations show a correlation between age, spin period, and magnetic field strength, illustrating how internal physics determines observable properties. Younger stars are fast-spinning with strong fields, while older stars are slower and weaker. You observe that cooling occurs concurrently with spin-down and magnetic evolution. Neutron stars lose thermal energy initially through neutrino emission from the dense core. As they age, surface photon emission dominates, and the star gradually becomes cooler and less luminous in X-rays. By comparing observed surface temperatures with theoretical cooling curves, astronomers infer the presence of superfluid neutrons and superconducting protons in the interior. These comparisons confirm models of dense matter physics and thermal transport in extreme conditions. Some neutron stars experience sudden changes in rotation known as glitches. These events are caused by interactions between the crust and superfluid interior. When pinned superfluid vortices suddenly unpin and transfer angular momentum to the crust, the rotation rate increases briefly. Glitch monitoring provides a direct probe of the internal structure, confirming the presence of a superfluid core and revealing the coupling between the interior and observable crustal dynamics. These events, though sporadic, accumulate valuable data on long-term neutron star evolution. You consider the behavior of neutron stars in binary systems. Accretion from a companion can alter spin and magnetic field. Material spiraling onto the neutron star transfers angular momentum, spinning it up to millisecond periods. At the same time, the magnetic field may be buried or reduced, producing weaker observable fields. Observations of recycled pulsars, which are old neutron stars spun up by prolonged accretion, demonstrate this evolutionary pathway and show how external factors shape the life cycle. In some cases, accretion can lead to X-ray bursts or even sustained nuclear burning on the surface. These processes provide insight into the composition of the outer layers and the physics of thermonuclear fusion under extreme gravity. By studying burst frequency, energy output, and spectral characteristics, astronomers derive properties of the crust and estimate accretion rates. The connection between mass transfer, energy release, and rotation highlights the interplay between internal and external evolution throughout the star's life. As the star ages further, pulsations become slower and less energetic. Older neutron stars may fade from view in radio, X-ray, or gamma-ray bands, becoming effectively invisible to most telescopes. The residual thermal emission continues to decline, and the crust gradually reaches thermal equilibrium with the cooler core. Observations of these faint neutron stars are rare but crucial for understanding the full range of evolutionary states. Surveys of isolated neutron stars show a spectrum of luminosities and rotation rates consistent with long-term cooling and spin-down models. You note that some neutron stars may ultimately reach a critical mass through accretion or mergers. When the mass approaches the Tolman-Oppenheimer-Volkoff limit, the internal pressure from neutrons and superfluid interactions can no longer support the star against gravity. In such cases, collapse into a black hole occurs. Observationally, the existence of high-mass neutron stars approaching this limit provides constraints on the equation of state of ultradense matter. Measurements of binary systems and merger remnants confirm these theoretical thresholds. The interplay between rotation, magnetic field, and energy loss also affects lifespan. Fast-spinning pulsars with moderate fields may remain active for tens of millions of years, while magnetars may exhaust magnetic energy more quickly, producing transient high-energy activity before settling into a quieter state. Observations of pulsar and magnetar populations allow astronomers to reconstruct statistical lifetimes, confirming models that incorporate spin-down, magnetic decay, and thermal cooling. These lifetimes are consistent with the observed distributions of periods, magnetic field strengths, and emission characteristics across thousands of neutron stars. You observe that even after rotational and magnetic activity diminishes, the neutron star remains an object of immense density and gravity. Its composition, dominated by neutrons and superfluid matter, preserves the record of its formation. Observations of faint thermal emission or gravitational effects on companion stars provide subtle evidence of their continued existence. The transition from an active pulsar to a quiescent, slowly cooling neutron star represents the final stages of a long astrophysical evolution, determined by fundamental physical laws. Occasionally, neutron stars merge, producing both gravitational waves and electromagnetic counterparts. These events reset the life cycle in a sense, creating new environments and, in some cases, resulting in collapse to a black hole. Observations of merger events confirm theoretical predictions of mass ejection, kilonova emission, and R-process nucleosynthesis. By studying merger remnants, astronomers link the life cycle of neutron stars to broader cosmic evolution, connecting individual stellar endpoints to galaxy-wide processes. Finally, you reflect on the diversity of neutron star fates. Some remain as isolated, slowly cooling objects for billions of years. Others interact with companions, evolve into millisecond pulsars, or produce spectacular bursts and flares before fading. The combination of spin-down, magnetic decay, thermal cooling, accretion, and mergers determines the trajectory of each star. Observational evidence supports these pathways, revealing a complex but predictable pattern. Following the life cycle from birth through spin evolution, magnetic adjustment, accretion interactions, and potential collapse, you begin to understand the interconnected physics that governs neutron star behavior and the final stages of their existence. You observe two neutron stars side by side, one a pulsar, the other a magnetar. Both are remnants of massive stars, but their properties diverge significantly. Pulsars typically have magnetic fields around 10 superscript 1 superscript 2 Gauss, sufficient to channel particles along field lines and produce steady radio pulses. Magnetars, by contrast, possess magnetic fields that can exceed 10 superscript 1 to 10 superscript 1 Gauss, driving occasional bursts and flares through magnetic stress and crustal activity. These differences manifest in rotation, emission, and long-term evolution, offering clear observational distinctions. You notice that rotation plays a central role. Pulsars are often born spinning rapidly, with periods of tens of milliseconds. Their rotation slows gradually as energy is lost through electromagnetic radiation and particle winds. Magnetars may also start with fast rotation, but their enormous magnetic energy dominates the spin-down process. Stronger magnetic fields exert greater torque, producing rapid deceleration and linking rotation rate directly to magnetic intensity. Observations of period distributions in both populations support this correlation. The source of energy distinguishes their behavior. Pulsars primarily radiate energy from rotational kinetic energy. As the star spins down, electromagnetic radiation diminishes accordingly. Magnetars, on the other hand, release energy stored in the magnetic field itself. The decay of the field powers persistent X-ray emission, flares, and bursts. This difference explains why some neutron stars remain visible for billions of years as radio pulsars, while magnetars exhibit episodic high-energy activity over shorter lifespans. Magnetic stress shapes surface activity. In pulsars, the field is strong but insufficient to fracture the crust regularly, so surface hotspots are relatively stable. In magnetars, magnetic stress exceeds crustal rigidity in localized regions, producing starquakes and sudden energy release. Observationally, this results in transient bursts and variable X-ray luminosity. Pulse profiles also differ. Pulsars exhibit regular, steady pulses, while magnetars can show irregular or intermittent pulsations due to magnetic reconfiguration. You consider how internal physics influences external differences. In both types, the crust and superfluid core interact to regulate rotation and field evolution. In magnetars, rapid field decay and Hall drift concentrate energy in localized areas, increasing the likelihood of flares. Pulsars experience slower magnetic evolution, maintaining more stable fields over millions of years. Observations of glitches, spin-down rates, and surface temperatures confirm these differences, providing insight into the interplay between interior dynamics and observable behavior. Accretion can modify the distinction between populations. Pulsars in binary systems may be spun up to millisecond periods, producing a different evolutionary track. Accretion can also reduce surface magnetic fields, producing weaker observable fields that mimic properties of older pulsars. Magnetars, however, are less commonly found in accreting systems, and their strong fields resist significant burial by infalling matter. Observational surveys of binary populations confirm these patterns, demonstrating the influence of environment on neutron star evolution. Thermal emission reveals additional contrasts. Pulsars typically cool steadily, emitting X-rays consistent with surface temperatures governed by standard neutrino and photon cooling processes. Magnetars exhibit elevated temperatures relative to age, maintained by ongoing magnetic decay and crustal heating. X-ray spectra show evidence of hotspots, variable luminosity, and thermal anomalies, indicating that internal magnetic energy directly influences surface emission. These measurements provide clear, quantitative distinctions between the two classes. The timescale of activity differs notably. Pulsars emit detectable radiation over millions to billions of years, with gradual spin-down and field decay. Magnetars, in contrast, have shorter periods of high-energy activity, typically tens of thousands of years, after which the field weakens and emission diminishes. Observations of magnetar populations show clustering in age, rotation, and luminosity, consistent with theoretical models of magnetic decay and energy release. These trends emphasize the importance of initial magnetic field strength in determining the evolutionary path. You observe that magnetic geometry affects emission patterns. Pulsars generally have stable dipolar fields aligned at some angle to the rotation axis, producing predictable beams and regular pulses. Magnetars may have more complex field structures, including multipolar components and strong toroidal fields. These configurations lead to variable emission, asymmetrical hotspots, and unpredictable bursts. Detailed timing and spectral studies reveal how geometry and field complexity shape observational characteristics, linking internal magnetic structure to detectable radiation. Population statistics reinforce these differences. Surveys of neutron stars show clear distributions. Pulsars dominate in number and longevity, with periods ranging from milliseconds to seconds and moderate magnetic fields. Magnetars are rarer, with higher fields and episodic X-ray activity. Observed correlations between age, rotation, and luminosity match theoretical predictions based on magnetic field evolution and energy dissipation. These patterns confirm that the fundamental physics of field strength and decay govern the divergence between pulsars and magnetars. You note that extreme events provide additional evidence. Magnetar flares release immense energy in fractions of a second, dwarfing typical pulsar emission. Observations of giant flares, soft gamma-ray repeaters, and X-ray bursts demonstrate the role of magnetic energy in driving these phenomena. Pulsars rarely show such events, confirming that rotational energy dominates their radiation. By comparing flare statistics, timing, and emission spectra, astronomers can clearly classify neutron stars and understand the underlying physics responsible for each type. Finally, you consider the broader implications of these differences. The contrasting behavior of pulsars and magnetars illustrates how initial conditions, mass, rotation, magnetic field strength, and environment determine the observable properties and evolutionary pathways of neutron stars. Observations across multiple wavelengths, from radio to gamma rays, combined with theoretical models of magnetic evolution, spin-down, and crustal mechanics, create a coherent picture of neutron star diversity. Following these distinctions, you begin to sense how individual stars connect to populations, cosmic evolution, and the fundamental physics of matter under extreme conditions. You take a moment to step back and observe neutron stars as they populate the galaxy. Each one is a relic of a massive star, compressed into a sphere only about 20 kilometers across yet containing more mass than the Sun. Their existence exemplifies the extremes of density, gravity, and magnetism. By studying them, you gain insight into physical principles that cannot be reproduced in terrestrial laboratories. The behavior of these compact objects confirms the predictions of general relativity, nuclear physics, and electromagnetism under extraordinary conditions. The diversity among neutron stars offers a window into how initial mass, rotation, and magnetic field shape evolution. Some become pulsars, emitting regular radio pulses over millions of years. Others develop the intense magnetic fields of magnetars, releasing energy through flares and bursts. By observing these different behaviors, you trace the influence of internal composition, crustal rigidity, and superfluid dynamics. Timing measurements, spectral analysis, and X-ray observations allow you to connect these phenomena directly to the underlying physics of matter at extreme density. You notice that the study of neutron stars bridges multiple scales of science. Microscopic nuclear interactions in the core determine macroscopic properties such as radius, mass, and moment of inertia. Crustal mechanics control starquakes and glitches, influencing observable rotation and radiation. Magnetospheric dynamics shape the beams and bursts that reach telescopes across the galaxy. Each measurement, whether pulse timing, luminosity, or spectral energy, links a local physical process to an astrophysical consequence, revealing the interconnectedness of forces and matter. Gravitational waves expand this perspective further. When neutron stars merge, ripples in spacetime propagate through the universe, carrying information about mass, spin, and internal structure. By detecting these waves, you observe phenomena that directly test general relativity and probe the equation of state of ultradense matter. The combination of electromagnetic and gravitational observations, multi-messenger astronomy, provides a more complete understanding of the physics governing neutron stars, showing how extreme conditions produce measurable signals across vast distances. You reflect on the balance of forces inside a neutron star. Gravity compresses matter to extraordinary densities, while degeneracy pressure from neutrons resists further collapse. Magnetic fields channel energy, create stress in the crust, and accelerate particles. Rotation introduces centrifugal forces and affects spin-down rates. Observations of spin, magnetic field evolution, and thermal emission allow you to quantify each contribution, confirming theoretical models. This balance illustrates fundamental physical principles operating at scales far beyond everyday experience. Thermal evolution provides further insight. Neutron stars cool initially through neutrino emission from the core, then through photon emission from the surface. Measuring surface temperatures and cooling rates informs models of superfluidity and superconductivity within the interior. Observed cooling curves match predictions from nuclear physics, confirming the presence of exotic states of matter. In this way, Distant stars become laboratories for verifying theories of particle behavior under conditions impossible to recreate on Earth. You notice that neutron stars demonstrate the role of time in shaping observable phenomena. Spin-down occurs over millions of years, while magnetic decay alters emission patterns on shorter timescales for magnetars. Glitches, bursts, and flares punctuate longer-term evolution, providing time-resolved information about the internal structure. Monitoring these processes over years or decades gives you a dynamic understanding of stellar behavior, allowing precise comparisons between theory and observation. Time itself becomes a tool for probing physics under extreme conditions. Accretion in binary systems adds further complexity. Matter flowing from a companion modifies spin, magnetic field, and radiation. Observing recycled millisecond pulsars reveals how external influences interact with intrinsic properties to shape evolution. Burst events, thermonuclear flashes, and long-term spin-up all provide measurable signatures of mass transfer, allowing astronomers to connect microphysics and astrophysics across time and space. The combination of isolated and binary neutron stars provides a holistic view of stellar life cycles. Magnetospheric processes link the internal to the external. Electrons accelerated along magnetic field lines produce beams and pulses detectable across the electromagnetic spectrum. Variability in these emissions reflects changes in rotation, field configuration, and crustal activity. Careful observations of pulse shapes, polarization, and spectral energy distributions allow detailed reconstruction of the star's magnetic geometry and dynamics. Each detected photon carries information about forces and matter inside the neutron star, revealing the intimate connection between microphysics and observable cosmic phenomena. You reflect on how neutron stars inform broader astrophysics. Their mergers produce heavy elements, including gold and platinum, seeding the universe with material essential for planetary systems. Their gravitational waves enable measurement of cosmological distances and verification of relativity. Observations of populations across the galaxy inform models of star formation, binary evolution, and galactic dynamics. In this way, each neutron star contributes to the cosmic story, providing insight into both fundamental physics and the evolution of the universe. The extreme conditions present in neutron stars test the limits of your understanding. Densities surpass nuclear saturation, pressures reach billions of times those in the sun's core, and magnetic fields distort atomic structures. By observing these stars, you validate and refine theoretical models, confirming the principles of quantum mechanics, relativity, and electromagnetism under conditions far removed from everyday experience. The universe offers a laboratory on a grand scale, and neutron stars are among its most instructive experiments. Finally, you consider your place as an observer. Studying neutron stars deepens your understanding of physical laws and their universal applicability. The precise measurements of rotation, emission, magnetic field, and gravitational waves reveal a cosmos governed by consistent principles, where extreme objects follow predictable patterns. You sense the interconnectedness of microphysics and cosmic evolution, of energy and matter, and of the smallest particles to the densest stars. As you rest, your mind can dwell on the calm precision of the universe, the subtle signals from distant neutron stars, and the certainty that science allows you to witness phenomena that both challenge and confirm the laws of nature.